203. And that would be minutes. Does that number make sense? How could you check yourself fairly simply? Yeah, you could go 600, and that's equal to 0 seconds, right? That's the beginning. And then you could go 22 minutes, and then what's here? 300. And then you could go 44 minutes, and then what's this? 150. And then you could go 66 minutes, 75. And you could go 88 minutes. What is it?
37.5.
Thanks. And you could go on 110.
Yeah. 18.75.
And you could go 130.
9.375.
154.
4.9.
76.
2.3.
98.
1.3.
And that's good enough, right? So we know that if you go 198 seconds, you're going to have 1.2 grams of this. And so if I go 203, I should get myself down to 1. Okay.
So when you're given that 600 gram sample,
Yep.
you know that the half-life is 0, that it's reached at.
No, this is time. We're letting the clock tick. So I give you 600 grams of it, and how long have you had that 600 grams? No time. So then I start counting, right when I get the sample, I start counting, and so I wait 22 minutes, and then I mass the sample out, and there should only be 300 grams there. Do we have a number for the second one? 7.38 grams. Does that number make sense? How many half-lives do we have? Ish. 6? Are we okay with about 6? It's about a half an hour, 27 minutes. So we have about 6 half-lives. So if I drop this 6 times, so 750 goes to 325, 375, sorry, 375 goes to 100 and 100 and what? Yeah, that's it. 187.5 to 93.8 to 46.9 to 23.4. 1, 2, 3, 4. That's 5 half-lives to what? 11.7. Okay, so once we've hit 6 half-lives, we're at 11.7, which is pretty close to 7.38. And it's not exact because 27 minutes isn't 30 minutes. So all we're doing is like, does this number make sense? If the number that we calculated was 112, you could be like, okay, I totally did something wrong. So everybody can calculate that out? Okay. How about this definition for a nuclear decay series? That's good. So each of the isotopes that are in the decay series are called daughter isotopes. And so the decay series is a bunch of daughter isotopes until finally one of the daughters is not radioactive anymore. We didn't quite get to this last class, but do we have an answer for this one?
Fusion's like
Too much information. Less. This is less.
It's an efficient way to generate electricity.
Oh, sorry. That's all we're doing. We are only boiling water. What's a coal fire plant do? Boils water. So unless we're talking about a solar plant or a wind farm or hydroelectric, what we're doing to turn the turbine is boiling water to make steam to turn the turbine. So a nuclear power plant is just a really, 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 really expensive water boiler.
And that's so that you can have the movement part
Yeah.
of
You guys watch that video? Do you remember those things?
I only remember.
I mean, do you remember Schoolhouse?
the one.
Schoolhouse Rock in general? I always remember that one and like conjunctions and those kinds of junction, yeah, the trains and stuff, yeah. So the point of that video is the point of this question. The entire point is to take that thing that we showed that picture of, that guy standing on top of that large piece of equipment, to make it spin, and that's it. So if we could get people to spin it, that'd be awesome, but there aren't people out there that can do that kind of thing, obviously. How about this last question here?
Fusion is combining two small nuclei to make one large nucleus. But it sounds like it's tough to control that heat, right? And then fission.
So this is, in chemistry, this would be like a combination reaction. I take two things and make one thing. And then, go ahead, the fission.
The opposite. Neutron enters a nucleus and makes two small nuclei.
This is kind of similar to a decomposition reaction in chemistry where one thing becomes two things. Okay.